Hi, this is Dr. Justin Esarey, and this week we're going to talk about CART methodology, classification regression trees, and random forests. CART and related methodologies are ways of taking a data set and building a decision tree using that data set that is capable of giving you good predictions of some dependent variable or correctly classifying a discrete or categorical dependent variable on the basis of the observable independent covariates. So the first question to ask is, what's a decision tree? Well, a decision tree is something that looks a little bit like this. Imagine, actually I'm going to do this first. Imagine we've got a data set, and that data set has some dependent variables in it. We'll start off by considering a dichotomous dependent variable, y and 0, 1. And it also has some independent variables, and we'll start off considering these continuous variables. So x might be inside of 0, 1. We'll say there's a z variable that also is inside of 0, 1, and a w variable that's inside of 0, 1. Okay, so a decision tree takes these variables and uses the three independent variables to make classification decisions about what we expect y to be, given x, z, and w. So for example, the first node might be x, and we might say, well, if x is greater than 0.5, we go down this part of the tree. And if it's less than or equal to 0.5, we go down this part of the tree. Then down here, we look at, let's say, z. So if x is greater than 0.5, then we ask, is z greater than 0.75 or less than 0.75? And maybe if we get this far, we can automatically say, well, if we get to this bin, then the probability that y equals 1 is something like a quarter, 0.25. But if we go down this tree, then we need to ask a question about w. And if w is greater than 0.1 or less than or equal to 0.1, we might be able to say, like, well, if you're on this node of the tree, probability of y equals 1 is, say, 0.8. And here, it's, let's say, 0.1. On the other end of the tree, maybe we don't immediately ask about z. Maybe z is irrelevant. We just ask about w. And I'm starting to lose some space here. But if we say, we're going to classify according to whether w is greater than 4 or less than or equal to 0.4 rather. And if it's greater than 0.4, we'll say that the probability of y equals 1 is a half. And if it's less than or equal to 0.04, we'll say the probability that y is 1 is equal to 0.9. So this decision tree allows us to sequentially move down the tree, looking at each node, making a decision based on what observation we have, and end up in one of these bins at the bottom of the tree. So if I, for example, have a particular observation where x is 0.8, w is 0.2, z is 0.4. Then what I do is I want to know, well, what's my guess for y? Well, I say, okay, x is greater than 0.5 because it's equal to 0.8, so I go down that node of the tree, or that branch of the tree, rather. Then I have the z node, and z is 0.4. That's less than 0.75, so I end up here. So my guess is that the probability of y equals 1 is a quarter. But what if, for example, we have another observation where x equals, let's say 0.6, w equals 0.4, and z is 0.8. Well, then we'd end up down this node of the tree again. Z is 0.8, so that's bigger than 0.75. We'd end up down this node of the tree. W is 0.04. That's that's greater than 0.04, so we end up down this node. And then our guess would be that the probability of y equals 1 is 0.8. So decision trees are a really simple way to explain prediction and classification decisions to someone who's not particularly sophisticated statistically, because it's so visual. It involves these decisions that are binary and pretty obvious. And it turns out that if we fit these trees appropriately, these guesses down here can be pretty accurate. And in addition, the bin structure can be such that the model that's implied by this classification and decision or regression tree can actually be highly nonlinear. It can be really adaptive, really flexible in terms of the relationships that it predicts. So the way that these decision trees make predictions via binning is by breaking the data set up into these particular bins. So each terminal node in the tree, so the end node in a tree, is just a particular bin. And if we call, for example, we'll call y hat b the estimate of y, or the probability of y equals 1, for bin B. Actually, I'm going to use uppercase here, so we'll call it bin B. Then our estimate of PRY equals 1 for bin B is just going to be equal to 1 over the number of observations in bin B times yi, or actually I should say sum of I in 1 to the number of observations in B, yi minus y average for bin B. Actually, I should say if y is continuous, and if y is dichotomous, it's just the number of yi in category C divided by the total number of observations in B and B if y is categorical. So in other words, if y is dichotomous, and we look in a particular bin and see that 50 out of 100 observations have y equal to 1, then the probability that y equals 1 is just 50 over 100, or a half. This is the fitted value PR y equals C, if continuous and if categorical. These are pretty simple computations. This is just an average, and this is just a proportion. So all we're doing to fit these predicted y hats is just take the average of the observations that we see in each bin. So again, that's really easy to explain to an outside observer or a non-statistician when you're trying to explain to them how you came up with these predictions. You said, well, we fitted this tree, and then we took what our observations were left in this tree, and we computed an average. So for example, going back to a simple tree here, if I had just one division, so one node, x is greater than a half or less than a half, less than or equal to a half. Let's suppose that y is dichotomous, just like before, and I had 20 observations for y equals 1 in this bin, and 30 observations for y equals 0 in that bin. That would mean that the fitted probability that y equals 1 for this particular bin would just be 20 over 50, or 2/5. In this bin over here, maybe the number of y1 observations is something like 5. The number of y equals 0 observations is like 70. So the probability that y equals 1 in this bin is just 5 over 75. If we divide this into its reduced fraction, 1/15. So that's all there is to it. This is pretty simple math when it comes down to it. The tricky part, of course, is not in interpreting the tree or explaining the tree, or even explaining how you get these predictions out of the tree, but fitting the tree. So the hard part is, where does the tree come from? And as it turns out, even that's not too hard. We can explain that pretty simply. So let's do that. How do we fit these trees? So CART is actually one particular method for constructing these trees. But all of these different methods share the same basic idea. They just differ on some of the particular implementations. And we'll go through a couple of different implementations to give you a sense on how these things differ. So we're going to go back to our previous example where we've got a data set with dichotomous, I want a dichotomous dependent variable. And for simplicity, I'm going to switch to all of the independent variables also being dichotomous. And we'll extend both of these frameworks in just a second so that the dependent variable and the independent variables can be categorical, multinomial, or continuous. But for now, just to keep things simple, we'll dichotomize everything. If we're trying to construct a classification regression tree, a decision tree for the dependent variable y, we have 3 choices for the first node, x, w, and z. So you can think of trying to compare a node, or a tree rather, that starts with this to a tree that starts with this to a tree that starts with this. And the question is, which should we pick? And how do we know that that's what we should pick? Well, just like a lot of different statistical models, we're going to try to pick the one that minimizes error or maximizes quality. And where the trick comes in is defining error or defining quality. And that's how, as I mentioned earlier, there are multiple algorithms for this. These different algorithms have different ways of assessing error. One way of assessing error when y is dichotomous is, or actually also or categorical, is entropy. Entropy is a measure of how much information is contained in a system or a variable. And for the purposes of CART, we define this. Cap C is the number of categories, so negative the sum over C of pi hat C times log pi hat C, where cap C is the number of categories in y, and pi c is the probability that y equals c in the data set. So if y is dichotomous, this works out to negative the sum. Actually, we don't really need that sum because there are only going to be 2 categories. Negative pi hat log pi hat plus 1 minus pi hat log 1 minus pi hat, where pi hat is the probability that y is 1. So that's entropy. Like I said, entropy is a measure of how much information there is in a data set. So this is computed over the entire data set before we do any partitioning. And as you can see, the more homogeneous the data set is, the the less entropy there is in a data set. So for example, going into this dichotomous case, suppose that all the observations were 1s, so that the probability that y equals 1 in the whole data set is equal to 1. Then what we have here is 1 times 0 plus 0 times log 0, which is, we're going to actually define for this purpose as being that quantity as being 0, so that would imply that the entropy is 0. The same would occur if pi were 0. So we've got, at both endpoints, we've got entropies of 0. In the middle, this term tends to get bigger. So, and it achieves a maximum, in particular, at pi equals a half. There we'd have a half times log a half plus, a half times log a half. Actually, I'm going to do it the same way, which is just log a half. And if you're interested to know what the log of 1/2 is, .69. I have seen cases where that's a base 10 log. I have seen cases where this can be computed. This is computed with a base 2 log, which is actually more appropriate given the fact that entropy is ultimately related to the number of binary bits it would take to encode this data set. It's a little bit more than I'd like to go into at the moment, but take my word for it, that's how it is. So we could compute the base 2 log of 0.5 instead, and that's -1. So -1 is +1, because we have to put a negative in front of all of this. Negative log a half is +1. So it goes from 0 to 1 to 0 with a parabolic relationship in between. Now, that's the entropy for the entire data set. What we want to do is assess which of these 3 choices gives us what's called the best information gain. And in short, what this asks is which of these partitions reduces entropy the most. So we need a way of computing entropy in a particular bin. And in fact, we do that just by looking at the probabilities in each of the bins. So this would be x1 and x0, something like that. We compute these probabilities for each of the possible bins, and then compute the sum of entropies in both bins. So for example, for this x case, what we would do is we would say, all right, the entropy after partitioning with x is just going to be the sum from j equals 1 to cap j times the number of elements in bin j, the number of observations, y in bin j, over the total number of observations, times the entropy in bin j where j is the total number of categories of x. In this case, it's 2, so we just have the entropy in bin 1 corresponding to x equals 1, and the entropy in bin 2 corresponding to x equals 2. The entropy in a particular bin is calculated the same way as the total entropy for the data set. So we can just sum over all the categories of y. I need to put a hat on that. What's the probability in bin j of, I'll put the j on top since the c is on the bottom here. What's the probability in bin j of being in category C times log of pi hat c in bin j? Sum that up over all the categories and you get the entropy in bin j. So compute the probabilities of being in each category in each of the proposed bins, and then weight by the total number of observations in each bin, or the proportion of observation in each bin, and sum up to get the entropy after x. And just to abbreviate this, I'm going to call this h of x. That's abusing notation slightly. The reason I'm going to abuse the notation in this way is because I want to write that the information gain for x is going to be equal to the entropy in j, I'm sorry, take that back, sorry, the entropy in the total data set minus the entropy after partitioning by x. Just like the total entropy in the data set, entropy after binning is smaller when these pi j's are close to 1 or 0, which tells us that the ideal partition is one where we are basically cleanly separating the data set into mutually exclusive and pure categorizations. So for example, if partitioning the data set by x caused all the observations in one bin to have y equals 1 and all the observations in the other bin to have y equals 0, that would be an excellent classification, and it would reduce the entropy in the data set to 0. So x would be very difficult to beat as a partition if it could do that, and indeed we wouldn't need to partition the data set any further because we've already removed all its entropy. But in practice, that's probably not what's going to happen. You're probably going to get something like, probability y equals 1 is 0.8, and then the probability of y equals 1 is 0.2 or something like that. So you're going to get some separation, but not complete separation. And that will improve on entropy, but still leave some variation for other variables to explain. So just to summarize, in order to decide which node should go first in this tree, you would compute the information gain for each possible partitioning, and then pick the variable with the largest gain. So let's suppose, counterfactually in this example, that that happens to be x. So we decide, okay, we've gotten this far. But now we want to know what comes next. What should I put here? Well, we've got two remaining options. We've got w and we've got z. And the process proceeds exactly as before. You take whatever data is contained in this bin. So there's data in this bin. Bx equals 1. Compute the entropy in this bin. Compute the information gain for w and z just in this bin. So just for that bin, compute the total entropy, and then compute the information gain, and then choose the partition with the largest. Choose the variable with the highest information gain. And then do the same thing. Oops. Over here, there's going to be some data in bin x equals 0. Do the same thing to this data separately. So compute the entropy for the data in this bin, compute the information gain for w and for z, and choose the variable with the highest information gain. The trick here, I mean, it's not really a trick, but the idea here is I can get different answers. So I can find, for example, that on the right-hand side, or I'm sorry, on the left-hand side, I may want to partition via w, but on the right-hand side, I may want to partition via z. I can get different information gains in different subsets of the data. Makes complete sense. So the entropy measure is not the only possible measure of error, as I noted before. The eponymous CART method actually uses a different measure called the Gini Index. This Gini Index is related to the Gini Index used to calculate, for example, the degree of economic inequality in a state. In the context of CART modeling, the Gini Index is just the sum over all the categories of y, pi hat c times 1 minus pi hat c, which if you multiply it out, you get the sum c and over 1 to c of pi hat c plus the sum from c in 1 to c of pi hat c squared. And by a basic property of probabilities, the sum of all the possible states of y, the sum of the probabilities of all the possible states of y, has to add up to 1 because y has to take some value in its possible sets, in its possible set of values. So here we just get 1 plus the sum c of 1 to cap c of pi c squared. And when we're deciding which partitioning variable to place first or second on a tree, we just pick the one that most reduces the Gini index. And so just as before, you would first begin by calculating the Gini index for the entire data set, and then for each partitioning variable, you calculate the Gini index inside of each bin and add up all the individual indices for the bin. Then just pick the one with the smallest Gini index. Pick the variable, I should say, that has the smallest summed Gini index. Now, you can see that this shares some characteristics with the entropy measure. For example, if, say, just counterfactually, that y has two categories, 0 and 1, so y is just dichotomous again. Then if a particular bin, if all the observations are equal to 1, so that the probability that y equals 1 is just 1, then this Gini index would be 1 times 0 or 0. If pi is 0, we also get 0 times 1 or 0. Either way, you get 0 at both ends. Also, as before, you get the largest value when this pi is equal to a half. So if the probability that y equals 1 is a half in a bin, your Gini index is going to be a half, times a half plus a half times a half, where each one of these categories, obviously we only have two in the dichotomous. We've got a possibility that y is 1 and a possibility that y is 0, so you add them up, and in this case you get a quarter plus a quarter or a half. So again, we get a maximum at the most diversity in the data set, sort of the same point we would get the most entropy in the data set. And so consequently, we do get similar results very often from entropy and Gini-based measures. But there can be some differences because of the way that each bin is weighted, for example. So we still have to use these weights here. Where am I? There we go. Oops. Oh. We still have to use these weights here when we compute the total gain, or Gini gain, as it were. So when calculating Gini index over multiple bins, e.g. By a proposed partition, what you need to do is sum up over all the bins. Oops. The Gini index times that, oops. There we go. You need to pre-multiply by that adjustment ratio, where the adjustment ratio effectively indicates what proportion of the data set is in each bin, multiplied by each individual bin's Gini index. So those weighting schemes are the same, but what's different is that the entropy may weight deviations from perfection differently than the entropy criteria, because even though they both have the same maximum and they both have the endpoints at 0, they both have minima at 0 and 1, the behavior in between, while similar, isn't necessarily exactly the same, and the relative heights aren't necessarily exactly the same. So you can get effectively different trade-offs among different variables, slightly different trade-offs, usually not huge ones, one would hope, but somewhat different trade-offs depending on exactly which algorithm you use. But no matter which algorithm you use, the basic idea is the same. You compute a weighted average of the Gini indices of the proposed bins, subtract that from the, well, if we call this, so if we call this the Gini index for the entire data set, and we call this the Gini index for the proposed division partitioning according to some variable x, then we're looking for which one gives us the biggest reduction in Gini index, or the biggest value g minus gx. With the hope being that gx would be like 0 in the perfect partition, and so the information gain, which is just the sort of reduction of the Gini index, would be the largest possible reduction, with the understanding that that hardly ever happens. We hardly ever get perfect separation. So the extension of these methods to categorical dependent variables is pretty straightforward, because we've already written all the equations for the Gini index and for the entropy-based error measure in terms of different categories of y, which can exceed 2. We get 3 or 4 or 5 categories. Similarly, there's really no difference in having categorical independent variables with more than 2 categories, because then we just simply split x into either, well, there are a couple of different things we can do. Let's just make a note. Categorical dv's is just trivially follows from our existing notation. Categorical iv's, you have a couple of different options. Option A is to split in binary fashion. So, for example, you can imagine having a node x where you split according to, this is a 1 and this is a 2 or a 3. If we assume that x has 3 categories, 1, 2, 3, you can split like that. And that's not the only split, of course. You could have alternatively split 1 and 3 and 2, or all kinds of different ways you could have split that. That's one way to proceed, and in that case, what you need to do is calculate every possible binary split in the variable and figure out which split gives you the best entropy improvement or Gini index reduction until you find the best one, and then move on to the next variable. So find a partitioning inside of x that has the greatest information gain before moving on to the next variable. So this is just sort of, it increases the complexity of increases the amount of time it takes to implement this process, because now we've got to check multiple partitionings of x before we can compare it to y or z or w or some other independent variable. I guess not y in the example we've been using. Another thing you could do is to split more than 2 ways. So you could have x split sort of 1, 2, 3, like so. And in that case, we're just generalizing the existing rules for calculating entropy or Gini indices for a dichotomous x into more than one, or more than dichotomous x, a trichotomous x, or a quadrichotomous x. A polychotomous x. And all the notation we've already written is robust to that possibility, and it sort of anticipates there being more than one more than one potential binning inside of an individual variable x. So that's also another way you could proceed. I suppose you could also, I'll stay in the black ink, try both. You could try binary splits and the j-way splits and see which one's better. You could also, if j is greater than 3, you could try two-way splits, three-way splits, four-way splits, and so on. The package that I'm going to show you in R will, I think, default to splitting binary, although I believe you can tell it to split more than two ways, but it defaults to wanting to calculate a binary split for a categorical, for a categorical IV. Another possibility is continuous dependent and independent variables. And I'll start with continuous dependent variables. This is a fairly easy generalization. We're still going to consider the error that exists in the data set and that is reduced after binning by the classification variable. But instead of using entropy or information gain, we're going to use our good old friend sum of squared errors. Like so, where y is the mean of y, and this is just the sum of squared errors. So this would be for the entire data set. We'll call this, the error for the entire data set. And then if you propose some binning, using a variable, an independent variable x, then you get an error for each category, for each bin of x. So you just sum over the number of possible bins. Like so. So in other words, if I want to partition according to x, I calculate the sum of squared errors in each bin that's created by x, and then I add those together to get my total SSE. And obviously, if I have more than one choice for binning, choose the partitioning variable that yields the largest reduction in sum of squared errors. So here's the whole data set. Here's the error according to x. We want big reductions, right? We want, ideally, this quantity to be equal to e for the biggest possible reduction in sum of squared errors. And then for successive partitionings, so for example, if we've already partitioned according to x, and now we're considering partitioning according to z, this would be, let's say, ex1, and this would be ex0. The error for the sum of squared errors for the x equals 1 bin and the sum of squared errors for the x equals 0 bin. So when we're looking at z here, what we're looking at is reduction in error compared to ex1. So what we would do is say, well, what variable z gives me the biggest reduction in error? And again, we ideally want this to be equal to ex1. So just in other words, when you're proposing deeper partitions of the data set, don't go all the way back to the root node. Don't go all the way back to the first node in this tree. Start sort of in the bin you're in and compute error reductions from there. Pretty easy, pretty straightforward, pretty much an extension of principles we've already learned in linear modeling, for example. Last but not least, what if we have continuous independent variables? Now, in this case, we can proceed pretty much the same way we already did. It's just that we don't have a natural automatic partitioning into bins the way we did when x was, or some other independent variable was categorical. We have to create those bins. So before we were dealing with this situation, we can't deal with that anymore, or can't use that anymore. We have to say, well, if x is bigger than x0 or less than or equal to x0, we need to pick an x0. And one way of doing this is to consider, for each potential partitioning variable, here's x. Imagine putting all the observations in the data set on this variable x in order from smallest to largest. And so we've got observations at a whole bunch of different points on this line, and there's one at the smallest and one at the largest. Now all the possible partitionings exist between these observations, right? We just sort of imagine all these partitionings as cutting up the observations as they are. Technically speaking, there is some variation, or there is some neutral variation in where we can put these splits, because if I've got two observations right here and here on the number line, it doesn't really matter if the split is here or here. It produces the same reduction in error. So I'm just imagining putting these splits midway in between each two observations. So those are all my possible splits. And then I can calculate the SSE reduction for every split. The best one becomes x0. That's how you pick x0. That's one way to pick x0, and a common way to pick x0. So again, computationally a little annoying, kind of intensive. Not not the most convenient thing to do by hand, but a computer can do it really, really quickly. And so there's really no barrier to doing that and figuring out which binning structure gets you the most error reduction. So continuous IVs and continuous DVs don't pose any problem at all. It's just that instead of, for continuous DVs, instead of calculating probabilities or proportions, we're calculating errors. We're calculating the mean. I should actually make a note of this. This is the mean of y in bin bj. So we're calculating bin means instead of bin probabilities, and then just subtracting all the finding the sum of squared errors inside each bin. For continuous independent variables, we're picking splits out of the potential universe of splits that are implied by our data in order to find the best one, rather than in the case of categorical IVs, relying on the natural pre-existing splits of the data to to give us this. And that's really all there is to it. That's all there is to CART modeling. It's just a kind of a computationally intensive way of designing these decision trees in a sort of recursive, or not recursive, but iterative improving fashion. I want to spend just a few minutes talking about why the CART model is more flexible or adaptive than a garden variety, say GLM model with no interaction terms or the like. A cart model is designed to choose variables according to how well they improve the fit of the model to the data set sequentially. And so as a result, it's capable of doing things like this. Splitting x according to some criteria greater than x0, less than or equal to x0. And then assigning z to each of the lower nodes. It can split at different locations in both of these areas. And the binning algorithm can allow it to say, well, perhaps going from less than 0 to, or I'm sorry, greater than 0 to less than 0 causes say a decrease in y in this case. So we might say the average y in this bin is like 2, and the average bin in this one is like 1. While the opposite happens in this case. Maybe here the average y is like 0, and the average y here is like 3. We can get reversals of direction. So here, as z is going down, we're getting a reduction in y. Here, as z is going down, we're getting an increase in y, in the predicted y. So nonlinearity is in some ways automatic in cart models. Because of the way that they're designed, each branch of the decision tree is allowed to sort of make its own decisions and be independent from all the other branches of the cart tree. On the other hand, just because it's capable of doing this doesn't mean it automatically chooses the optimal model in some way. Let me give you an example of what I mean. Cart models are greedy models in the sense that they try to, at each successive step of the algorithm, they try to make the biggest improvement possible. In other words, they try to choose the partitioning of x and z that will cause the greatest reduction in sum of squared errors, the greatest reduction in entropy, or so on. Well, let me give you an example of a case where that approach would not, wouldn't work so well. So let's see. Do I want a pen? Yeah, I'll get a really thick pen here. Suppose I got two categories. Y is 1 or y is 0. And I'm going to denote y as 1 with this red pen color here. And I'm going to denote y is 0 with some other color, maybe something like, this blue. Coloring there. Okay, so I have two variables, x and z. Let's say this is x and this is z. Okay, now if we were trying to determine how we should split this dependent variable, so remember the red is y is 1 and the blue is y is 0. Okay. If we were trying to classify y as accurately as we could, the best way to do it might be to say split z right here at, we'll call this z0, and then now we've got two branches, right? We've got branch A where z is less than z0. We'll call this 0 there. Make that the 0 point. So z is less than z0, and this is z greater than z0. For z less than z0, we want to partition x here at x, 0, 0. And for here, whoops, what happened to my lines? We want to partition it at x, 0, 1, like so. Oh man, got stuff disappearing all over the place. There we go. Can I send this to the back? Yeah, it might be that. Oh, I just caused that to disappear. Awesome. Okay, let's try this again. Red, that. And this time I'm not going to color it in so much. I'm just going to kind of outline it like this. And then just put a little bit of color in here. Okay, so recalling that this is the y equals 1 space. We're going to cut this here at x0, or at z0 rather, and we're going to cut you stupid pen. Oh, jeez. Okay. With this division, we get perfect classification. This bin here, defined by z is less than 0 and x is less than x0, 0, is purely red. The same for here, for x is greater than z0 but less than x1, 0. Similarly, when z is greater than or less than z0 but greater than x0, we get a pure blue or y equals 0 case, and the same down here. But you'll notice that the way that we constructed this classification was to divide first on the variable that actually was not very effective at classifying in the first stage. In other words, in the first stage we cut according to z0, and you'll notice that when we did that, we created 2 blocks that were about half, this one might be, I don't know, a little less than 2/3 red, and this one's maybe 1/3 red. Not a very good reduction. We could have gotten a much better reduction in error, for example, classifying things in this way. It really depends on exactly what the case here is, but I'm going to guess this is the best division. Let's try this again. I want to use a brighter color. We'll use green. We'll use a slightly thicker one. No, green's not showing up very well either. How about purple? There we go. So if I had first classified right here on the x dimension at x0, 0, I could have put all of this blue category in one and almost all the red in another, but with some degree of error, right? And then when I went to classify with z, I'd try to split the space in such a way that I get the purest classifications possible. And so on this side, there's really nothing I can do. No split on z is going to improve in any way upon what I've already got. Over here, I could probably split right here. Like that at z0. And now what I've got is I've got 3 blocks instead of 4. I've got this block right here. Let's maybe see if I can get a little bit thicker. I've got that block right there. That's pure blue. I've got this block right here. that's pure red. And then I've got this block right here, which is, oops, let me go right here. Not pure anything, but mostly red. Some blue in there. The difference is that the greedy algorithm classified by X first, and therefore it was doing the best it could on the first iteration, but it was actually depriving itself later on of a more optimal division of the space, a better classification regime. So the point I'm trying to make here is that yes, it is the case that these cart trees can be highly nonlinear, which is good. It allows them to adapt to more spaces. But the way that they're constructed can actually cause it to do worse than it might if it were more intelligent about choosing its splits in advance. At least the basic cart algorithm has this property. And so we can't necessarily expect it by magic alone to always detect the right form or the optimal structuring of nonlinearity so as to catch the nonlinearities we would like it to in the data set. Which is all just a way of saying that it may be the case that cart methodologies are adaptive and nonlinear, but they still have their limitations. The greedy algorithm by which they are constructed may cause it to go down alleys which at first seem promising but actually are less optimal in the long run than other options might have been. And so one way we might think about improving on this is to not lock ourselves into just one tree. Maybe we want to try lots of different kinds of trees and get a sense of which ones do better and which ones do worse. And maybe combine their choices in some way to give us a better answer overall. And so that leads us into the possibility of a random forest. So now let's talk about random forest models. Now, you might have noticed that if we have a set of variables, x and w and z, we might have tons and tons of these independent variables that we can use, q, s, whatever, to partition and predict the dependent variable y. Should we use them all, or should we only use some of them and then stop? We can decide just to use them all no matter what, but that sort of leads to a potential danger in these cart models and also in the random forest models that we're going to talk about shortly. And that danger is overfitting. So it might be the case that, for example, a cart model is too good. It could be the case that I've got some kind of relationship between x and y here. I don't want my cart model to create a bunch of bins like this and then predict okay, in bin 1, that's my prediction there, and then in bin 3, that's my prediction there, and in bin 2, that's my prediction there. That's overfitting. That's too good of a fit. So there are various ways to fight the overfitting problem, and one of them is to ensure that your tree doesn't get too large. So one way to proceed is to grow a tree to its maximum extent and then prune. Tree pruning is the idea of selecting branches of a tree which don't improve very much on the entropy reduction or sum of squared errors reduction or Gini Index reduction. So imagine we've got 3 variables, x, w, and z, that we're using to grow a tree. And we grow some tree on them, and we grow the maximum extent possible. So we might put w there and z there, and these all have, I'm assuming, dichotomous splits for each of the variables. W and then I get bin predictions for each of the bins that result. 4, 5, 6, 7, and 8. All right. Now, pruning says what we should do is look at the smallest reduction in error that we get from any of these partitions. So probably that's going to be one of the lowest nodes in the tree. In fact, it almost is guaranteed, but almost by design to be. So let's say this partition gives us some reduction in the error metric of epsilon. What we might do is say, well, we're going to remove all branches with an information gain, with an error reduction of epsilon with information gain less than epsilon plus 1 standard deviation of epsilon, something like that. So there are all these information gains that accrue at every node. Here's like E1 and E2 and so on. This is the smallest one, but there's a bunch of them. We calculate the distribution for all those information gains, for all those reductions, and then we say, okay, there's a standard deviation to that distribution. We're going to prune all the branches that are within 1 standard deviation of the smallest error reduction. That might only be one branch. It's pretty much always going to be the smallest branch, right? The least error reduction branch. So we're always guaranteed to prune at least a little bit, as long as we're not... sometimes you can also specify that the error reduction has to be, a certain absolute small size before you prune it. But if we're just always going to prune the smallest one, you'll at least get rid of one. So we might just get rid of one. We might also get rid of an entire big branch. So we might get rid of all of these if, for example, this error associated with W here, called error 5 or something, is too small. We might get rid of this whole branch, and so we might end up with a kind of a lopsided tree. That's possible too. So pruning is a way of making sure that the error reductions that happen are big enough to matter. We're not just fitting data points one by one. The flip side of this is instead of pruning, we can prevent branches from growing in the first place. With a minimum error reduction requirement. So we can simply say a branch of a tree will not be grown unless the best option for growing it is bigger than some minimum criteria for information gain. We specify that criteria as a proportion of the total entropy in the data set, like 10% or something like that. We just fix that, and that's how we're going to proceed. So in that case, while you're growing the tree, so we'll go back to this example here. Let's say the first tree, it's the first branch, it's fine. We end up with 2 bins. And then the second branch, we're considering, okay, which variable should we put in here? Should it be W or should it be Z? Well, suppose that neither one of these variables produces very much information gain in this node. It produces less than, say, 10% reduction relative to the total entropy in the entire data set. We might just decide it would be better off not growing that branch in the first place. Just leave it. And once we decide to leave it, it stays. We might continue to grow these other branches. Oops. Like so. And just never fill out that branch. We might stop at certain branches. We might choose not to grow this one, but to grow that one. That's a possibility as well. So this is sort of forward-thinking pruning. It uses a minimum error requirement rather than growing the tree out to its maximum extent and then pruning back. So either of those approaches are feasible for trying to attack the problem of overfitting. Another possibility, or at least another way of trying to assess the potential of overfitting, is to separate training and test data. Now this doesn't have anything to do with how we grow the tree, but rather the data that we use to grow the tree. So if we've got a data set of 1,000 observations, what we might do is say, okay, I'm going to use 700 or 600 of these observations to train the model. So I'm going to fit the model on those. But when I go to assess how well this model actually is performing, how well it fits, I'm going to use the remaining 200, 300, 400 observations that I saved, that I held back, with the idea that you can't overfit on data you can't see. So when you're fitting these models, if you're trying to assess after the fact whether they have been overfitted, it might be advisable to hold back a section of the data, not train your model on that data, and then use that as the so-called test data to assess the fit of your model. And we'll see examples of that when we look at a model assessment in R. So a random forest is an idea that starts with the CART framework, the classification regression tree framework, and just says, well, one's good, maybe 1,000 will be better. Maybe we can grow a whole bunch of different trees, and the collective wisdom of all of these trees will in some way be better than any of the sum of the parts, or be more. I didn't say that very well. The forest will in some way be better than the sum of its individual tree parts. Now, of course, we've got to do something so that the algorithm doesn't just grow the same tree 1,000 times. You may have noticed that our previous description of CART made it pretty clear that for any fixed data set, as long as the algorithm is working properly, you just get the same tree over and over. It's a deterministic process. So we're going to have to do something in order to permute either the data or the partitioning variables available in order to make sure that we get different trees when we do it multiple times. And in fact, we're going to do both of those things in the usual random forest algorithm. So to grow a random forest, you do the following 4 steps. First, you create a whole bunch of bootstrap data sets. We'll say M many. Bootstrap with replacement. Data sets. Each one having the same size as the original data set. Now, this is not a lecture where I'm going to talk a lot about bootstrapping. I'm going to just assume that you know what bootstrapping is, and if you don't, you should watch one of my other videos that talks about this. But just to briefly refresh your memory, if I've got a data set with a few observations in it, let's say 5 observations in it, here are my observations. Bootstrapping with replacement involves randomly selecting a bunch of these observations to create a new data set. And with replacement means I can select them more than once. So imagine I roll a dice with 5 sides, 1 to 5 marked on the sides. A 2 comes up, and so this becomes my first observation in my bootstrap data set, number 1. I might, by chance get that same observation again. I might get another observation for the 3rd one. So if I mark these here, 1, 2, 3, 4, 5, so we can keep track of which one we've got. I might have 2 twice, and 4 here. And I might get 1 here, and I might get 1 again, and that's my first bootstrap data set. And then I do this a whole bunch of different times, and each time I'm rolling a dice to figure out which observation I'm going to get. And that's it. I just keep doing that over and over again to get a whole bunch of data sets. And M should be large, something like maybe 1,000 or 5,000. Okay, so I've got my M many bootstrap data sets. The second thing I want to do is for each data set, randomly select a subset of input variables on which to build the tree. And this set should be smaller than the total number of variables in the data set. So if I've got, say, k many IVs that I can choose from, I might choose, k less than k for each data set to fit, to use, to grow my tree. And those little k, I shouldn't use k twice. Let's call this P's probability. How about Q? Q less than K. Q should, the Q variables I choose for each data set should be different for each of my bootstrap data sets. So I've basically got different data going into the process and a different limited subset of independent variables, or independent IVs going into each one of these processes, each one of these cart growth processes. Then in step 3, I just grow a cart tree as usual. On the data set, on each data set. And I should use all the inputs I have. No pruning or limitations or a sort of minimum error requirements. In short, I'm going to exhaust my set of Q input variables, even if the last input variable causes a very small change in entropy or sum of squared errors or whatever my relevant criterion here is, Gini Index or whatever. And then finally, using the entire forest for any value of independent variables x, so I've got a vector of x variables here, call that x0. I calculate my prediction for y, the independent or the dependent variable, as equal to the average of all the tree's predictions. So, in short, what I'm doing here is just growing a whole bunch of different trees on slightly different versions of the data set and slightly different sets of input variables. And then in order to make a prediction for y for some particular location in the independent variable space, I compute a prediction for every single tree in my forest, and each one of those predictions becomes sort of akin to a vote. And then I average all of the different predictions to create the overall forest's impression or sort of prediction for the model. Hopefully this process will produce predictions that are a bit more robust and a bit less sensitive to peculiarities of our sample data set, because we're creating multiple samples out of our original sample, and because we're allowing the set of input variables to vary a bit. So hopefully we get some variation in which variables come first and which nonlinearities are identified and so on. This might take a long time, depending on the size of the data set and the complexity of the model. But hopefully the predictions that we get are better. I should also mention that some algorithms, including the one that I'm going to show you in R, compute errors using an out-of-bag sample. So some cases may be left out of each bootstrap data set to create an out-of-bag sample that will be used to compute classification error or regression error for the tree. So this is the basic idea that if I want to see how well my tree predicts, I shouldn't necessarily always use in-sample prediction. I should save some of my data out, not fit the model on that, and see how well the model does on that sort of pristine test data that I haven't trained my model on, and see how well I do in that sample. So the out-of-bag sample just says, well, when I create my bootstrap samples, for each one of those samples, I'm just going to like save the last 20% or 30% of the data, not train my each tree in my forest on that data, and then I can use that out-of-bag sample to figure out, okay, how good is the prediction error for each one of these trees, and by consequence for the entire forest. So that's all there is to it. It's a computationally intensive procedure, obviously, but it's one that, as long as you have the computer fast enough or the time to let it run, hopefully will improve upon the single tree methods that we talked about in the previous example. So let's talk a little bit about how we actually estimate these CART and random forest models on live data sets. And in order to do this, I'm going to load remotely from the interweb a data set on Titanic survival. I've actually written about this a little bit in my blog, and you can see some of these analyses in my blog post from a while back. The Titanic data set has information about people who survived and died on the Titanic. You can see right here. It has some kind of irrelevant information from our perspective, like their names. I really don't care too much whether whether John Jacob Astor lived or whatever, but at least no more than I care about anyone else living, and it's statistically not especially relevant. But what's interesting about them is we have information about their sex, what class they were in, whether they were a first, second, or third class passenger, which is a proxy for their wealth, whether they survived or not, their gender, sex, their age, whether there was a sibling on board, and whether they were parents and children on board. Some weird stuff like their ticket number and their fare, their cabin, where they got on, if they made it out in a boat, which boat they were on, and where they were headed to. For the purposes of our analysis, we're interested in predicting whether they survived or not, with the idea that we're looking for whether there were gender or sex, age, and class effects on who survived. Was it all the millionaires? Was it all the women? Was it all the children, or what? So we're going to start off by dividing the data sets into two groups randomly. I've used the order statistic here to just create a random ordering of the variables. And the first 655 cases are going to be my training data, when I'm going to fit my model to this data. And the remaining cases are going to be my prediction data that I'm going to use to assess my model. So what I'm going to do to assess the model is I'm going to start off with a really basic, just a logit GLM, nothing fancy or special. And I'm going to regress on class, sex, an interaction between class and sex, age, and whether there were siblings on board. And I'm going to fit this only on the training data. So if I do this and I look at this, what do I find? Well, as you already know, probably, the coefficients are not direct indicators of the substantive magnitude of the effects that we've estimated, but more likely than not, they are good indicators of the direction. There are some rare cases when the direction is actually not right either, but usually the direction is right. And what do we find? Well, you can see it's actually broken that class variable up into a factor, so it's broken into dummy variables for second and third class. And being in second and third class was bad from the from the perspective of survival. And in particular, you were more likely to die if you were in second class compared to first, and even more likely if you were in third. Being a male made you more likely to die. Being older made you more likely to die. Having siblings on board made you more likely to die. And there is possibly some interaction between the class and male variables. And in particular, you can see the effective gender is not as pronounced in third class. That could be because women and men both died in third class, which would indicate basically that everyone died. There was no women and children may have been first, but when it came to third class passengers, it was just they all died because class was an overriding factor. I can assess this model in various ways. I'm not going to plot the marginal effects for this model because this is I'm not really interested in that for the time being. What I am interested in is what percentage of survivors I can correctly predict and which percentage of fatalities I can correctly predict. So this uses the percent correctly predicted statistic, which we're not going to talk about. Actually, going to follow up later with a lecture talking about various fit statistic assessments, including the PCP. But for now, just it suffices to assert that I'm going to calculate the PCP, both in sample and out of sample, for survivors and for survival predictions and for death predictions. And what did I do wrong? I didn't actually perform the predictions. I need to do that. So let's try this again. Okay, so I've got in and out of sample predictions. In sample, I'm predicting 81% of the survivors correctly. So 81% of the people I say are ones really are ones. If I say they lived, they really lived. And about 80%, 79.7% of people I say died actually died. In sample. My out of sample predictions are, as you would expect, not quite as good because I didn't fit the model on this data, but they're pretty close. I'm predicting 74% of the survivors correctly and 78% of the deaths, the dyers correctly. So not bad. It's a good baseline on which to assess the other models here. You can also use this heat map statistic to assess the in-sample fit for the logit model. It takes a second to run because it actually has to go through a bunch of bootstrap predictions to work. This is the heat map fit statistic that's described in my paper with Andrew Pearson, Political Analysis, this year, maybe last year. And the idea is on the x-axis you've got what the model said the probability of survival should have been, and on the y-axis what you have is what the actual probability of survival was in cases that had similar probability assessment. So in other words, if the model fit is good, if I said you had a 40% chance of living, all the cases that had a 40% chance of living, about 40% of them should have lived. So a perfect fit is a 45-degree line shooting out of the origin here. And what you can see is the heat map fit statistic is actually pretty close to a 45-degree line. Furthermore, the coloration of the line indicates to what extent any deviations from perfect fit can be attributable to sampling variance as opposed to actual misspecification or a problem in the fit. Lighter values are better, and this line is, light all the way through. So, in short, this is a really good model. I can also use some commands to do the same heat map fit statistic on the out of sample. The only thing I lose is I don't get the bootstrap p-values, so I don't get an assessment of whether any gaps are attributable to chance or sampling variation, or instead attributable to misspecification. So this is the same plot, just without the coloration according to p-value. And what you can see is, again, even out of sample, we're doing pretty well. We're slightly under predicting the chance of survival for some people. So in other words, I'm sorry, over predicting chance of survival. So of the people we set at a 60% chance to survive, only about 45 or 50% of them actually survived. Of the people we said had an 85 or 90% chance of surviving, only about 80% survived. So the model is not perfect out of sample, but still quite good. Now let's look at a cart model. Let's build a tree. So the library that I'm going to use to build a conditional tree here is the party library, which is a lot less fun than it sounds. And the syntax for building a cart tree is pretty similar to the syntax for running any model, like a GLM model. I just tell it, here's the formula. I make survival a factor because that identifies this as a classification problem as opposed to a regression problem. And then I tell it I want to do this on the training data. And if I plot the result, it actually shows me a nice tree. You can see, though, that the tree is kind of getting jumbly because, in short, there's too much text and things are kind of getting crunched together. So what I'm going to do is I'm actually going to open up a PNG file that has a sort of bigger dimensions, and I'm going to plot that same tree into that survival plot area. And then I can open up a PNG file that's just been created in my directory. So let's see what that looks like. All right, so here's the directory, and you can see the Titanic tree.png was created. Oh, and it looks like it's still a little bit jumbled up. So maybe I'll go back and I'll expand the width and height a little bit. Maybe give it 600 pixels in every dimension. And let's try that again. Getting closer to separation. We still have a little bit of overlap here. So I'm going to clear this actually. Clear all the plots in the history. And maybe go for 700. And now take a look. Yeah, that's okay. So what do we see here in this tree? Let me actually just blow this up here. All right. So what we see is that the cart first identified sex as the most important variable, with men and women having different chances of survival. And the next thing it did was identify class as being the next most important survival characteristic. In particular, we can see that it breaks the first from the second and third classes in the men case, and the third from the first and second classes in the women's case. So for women, if you were a woman in first or second class, you were almost certain to survive. There were 121 people in this node, in this bin, and over 90% of them survived. Among the third class women, the odds were not quite as good, but actually not terrible. About 50% of the third class women survived. Among the men in first class, if they were young, which is to say, I'm sorry, this is, no, it's, less than or equal to 54. So if they were young, they had about a 50% chance of surviving. So young, rich men had a shot. Older, rich men were almost certain to die. So were basically non-baby, non-toddler men in second or third class. And the babies, even if they were in second or third class, had a decent shot of survival, maybe a little under 70%. So what this is finding is that there are some significant, what we would call interactions here. For example, you can see an interaction with age. Among the first class men, there was an age threshold, but it was far higher than for the second and third class men. For the women, there was no age effect. It was all about what class you were in. There was also a class effect for men that was contingent on age, and the class effect was also not quite as strong. The difference between the first class and second class Wasn't quite as strong if you were 3 years old. If you were less than 54, there was definitely an effect there. So it's teasing out some significant nonlinearity. We can generate in and out of sample predictions for these models using the predict command. And if you do the predict command, what you can see, let me see if I can just show you what this looks like here. If you just do the predict command on the survival tree, and I'm going to just show you the head of this matrix. You can see what it does is it actually gives you, for each observation, the probability of being in each of the classes. But there are only 2 classes, live and die, survive or not survive, with not survive being the first class. So it gives you this big old list with 2 numbers in each entry. So we have to unlist that and then pick, if we just want the survival probabilities, only every other number in that unlisting command. So that's what this little block of code here does. Then I can just compute % correctly predicted using the predictions I just made with the code I had earlier. What you can see is that the CART model out of sample is pretty much doing the same out of sample as the Logit model did. If you go back to the Logit model predictions, let's see, 74% of the survivors, 78% of the deaths. Here we're getting 72% of survivors and 82% of the deaths. Not really terribly impressive, although it is detecting some nonlinearity, which which was present in the data set, which is encouraging. We probably made our Logit model look a lot better by including that sex-class interaction term, which allowed there to be flexibility, allowed the effect of class to be contingent on sex. And we probably could have done even better if we thought about interactions with age, because you could see from the CART plot that there seemed to be an age effect going on as well, at least among men. If you were a lower class passenger on the Titanic and you were a man, you were only making it out alive if you were a toddler. Whereas among women, there was no effective age. For the richer men, it was basically anyone who wasn't be considered like above middle age, 54, 55. All right, so now, and I can do the heat map assessment as well. And this just creates a plot similar to the one that we created for the Logit, the heat map plot. And what you can see is that, as we would expect, I've jittered these a little bit. You can see I've jittered the rug. I've got bins here of predictions that correspond to the end entries of the tree. And these bins are sort of present on my x-axis here. And so I'm interpolating to some degree between these bins with my lowest fit. But the patterns look very similar. I'm still slightly over-predicting survival for these groups. And over here, I'm still slightly under-predicting survival for the lowest probability groups. But the general gist of the fit is out of sample, at least. This is out of sample fit, is the same. And indeed, if I compare the Logit predictions to the CART predictions, what you'll see is, so the Logit predictions are on the x-axis, the CART predictions are on the y-axis, and I've divided this into 2 groups because you can think about classifying people as living or dying depending on whether they're above 50% or below 50% predicted probability of survival, which is how I generated the PCP statistics. So what you can see is the people that the Logit model predicted to survive are, generally speaking, also the people that the CART model predicted to survive, with the exception of this group here. The people that the CART model predicted to survive are, there is a substantial overlap with the people that the Logit predicted to survive. So here's the conditional Logit, here are the Logit survivors here on this thing. Here are the, in the upper half, here are the CART tree survivors. So the ones that both were predicted to survive are in this upper right-hand corner. The ones that were both predicted to die are in the lower left-hand corner, and the misclassified cases are in the upper left or lower right-hand corners. And there are some misclassified cases here in both corners, but generally speaking, the predictions are somewhat similar. Now, we're going to grow a random forest. And as you might expect, because this takes because we're growing 5,000 trees, this actually takes a little bit of time. But this data set is small enough. Actually, it's already done. And the syntax for doing this is pretty similar to the syntax for the C-tree model. This is a different package. I'm using the random forest package. But just as before, I can specify a formula. Just like I did before, I specify the data to be the training data. I tell it the number of trees I want. Importance equals true. We'll save this statistic called variable importance, which I'll show you in just a second. And I just tell it if there are any missing variables, missing values, just to drop them or omit them. So I've fitted my model. The first thing I can do is create a variable importance plot. Now I've included a little bit of text in my code to talk about what this variable importance plot is. The variable importance plot uses the out-of-bag sample that we talked about. And what we do is we look at the prediction accuracy with all the variables and then with all the variables less 1. So as I mentioned, in a random forest, we only select a number of predictors for each tree that's less than the total number of predictors. So that allows us to assess how well these trees do with and without a certain variable being present in the out-of-bag cases. And the more important a variable is, the bigger the gap between the trees that include the variable and the trees that don't include the variable. And as you can see, the biggest gaps are with sex. The trees that don't include sex as a variable have the biggest decrease in accuracy from dropping sex, and they also have the biggest decrease in Gini purity. Gini purity is just basically it's a, let's see, how do I put this? Well, I can just read off the part where it talks about it. The second measure is the total decrease in node impurities from the splitting of the variable, averaged over all trees. For classification, the node impurity is measured by the Gini index. For regression, is measured by the residual sum of squares. So this second characteristic uses the Gini purity on the, I believe, on the in-bag sample. And the first statistic uses the prediction accuracy on the out-of-bag sample. In both cases, sex is the most important variable. Class and age are sort of contend for being the next important variable, and then the sibling variable is a distant fourth. We can also create marginal effects plots using the partial plot syntax. So the first thing I do here is create a training data set that excludes all of the missing values, because the partial plot command doesn't like missing values. So I create a data set that has those missing values removed. And then I ask for partial plots using the missing value free prediction data on, say, sex. And which class tells me which category of the dependent variable I'm predicting marginal changes into. And in this case, I want the class to equal 1, which is survival. So what this is telling me, this plot is telling me here, is that being a female causes a significant increase in my probability of surviving the Titanic, whereas being a male, as you might expect, causes a significant decline in the probability of surviving. Now, we can look at the partial plot help file here to get a sense of what it's actually showing us. The function being plotted is the fitted prediction for x, where you basically hold all the other variables in the regression constant. The sum end is the prediction regression function for regression, and the logits, log of fraction of votes for which class for classification. So going back to this plot, so what it's actually showing here for a logit is the difference between the log of vote fraction of the trees, classifying, for example, the female as survived minus the fraction classified. I go back to the help file just here for a second. Minus the classified fraction of classified having survived I'm sorry, minus the fraction having died among women. So a positive number means that the log of the ratio of survivors to people who died is positive. In other words, this is the effect on the log odds ratio, I guess is what they're really computing here, is positive. The effect on the log odds ratio of the men is negative, which means that the log of the probability, the predicted probability that a man died is less than the log of the probability that of a man living is less than the probability of the man dying. So we can probably actually even get a sense of backing out what this must have been. So if, for example, the probability that a woman lived was 80%, and we subtracted that from the probability that they died, you'd get something like 1.38, which is a little more than we get here, but you get the idea. For a man, if we just reverse those fractions, we get something like negative 1.38, which is actually not big enough, so we may need to reduce this down even more. And now we're getting about right, 2.19. So if they have a 10% chance of living and a 90% chance of dying, you get something like this. So it's a bit odd in my mind because I'm not used to thinking in terms of probability ratios, but the marginal effect is there nonetheless. And what you can see is that being a woman helps your odds of surviving, and being a man drastically reduces them. If we look at class effects, we can see that being in first class had an increase in your probability of survival and your odds ratio of survival, whereas being in second or third class decreased your odds of survival. And then finally, we can do a partial plot for age. And what we see here is that age seems like it has a bit of a weird effect. I'm going to try reducing the number of points in the age plot, see if that improves the quality of it. Yeah. Seems like there might be some significant nonlinearities in this age function that we may not be fully accounting for. So what I'm doing is just dialing up and down the number of points at which this age function will be calculated. Now 12 is obviously too many. If we do 9, we get something that looks a little something like this. So in general, what we're finding is that increasing age decreased your probability of survival. But it may be the case that certain age groups were more prone to survive to death than others. So that's a 6-point plot. This is just pretty much shows that the best survivors are kind of the toddler-aged people, or actually not toddler, a little older than toddler, like 10, 12-year-olds. If we put 8 plots in, we get the biggest dip here in the 70s. That might be overfitting, actually. If we get 10 points, we get this, showing big dips here right before 20 and then right after 70. We decided that 10 was already more than this plot was really willing to display. So if we get down to 4, yeah, that's a very smooth plot, but probably covering up a lot of the variation. So age in general has a declining effect on your probability of survival, but there may be some significant nonlinearities in that regression. We might, in fact, want to consider setting other variables equal to some constant in a way consistent with the tree. So remember from the tree that among men, age had a different effect for the first-class passengers than the second and third-class passengers. So we might want to maybe try holding some other variables constant. I believe that we can do that. Let's see. Class to focus on. Weights. Nope, it's just going to hold all other variables at their constant, or at their, I'm sorry, at their mean. Actually, no, it's gonna just compute it separately. It's not going to hold them at their mean. It's going to compute it separately for each observation, given what it actually what it was actually used for, or what its actual value was in the data. So some of these nonlinear are just going to be hard to squeeze out of there. So age is somewhat complicated, but we can, generally speaking, we can say the older you were, the worse off you were, but there may be some complex nonlinearities owing to class. Let's see how the network does in and out of sample in terms of predictions. So we're first going to look at the PCP, and I neglected to mention this before, but the PCP cutoff I'm using here is 0.5. So all observations with a predicted probability of survival greater than a half are classified as survivors, less than a half are classified as deaths. And we're looking at, out of sample, 76% survival correct predictions, 80% death correct predictions, which is only slightly better than the logit model. And if we do our heat map plot for the random forest predicted probabilities of survival, we see pretty much the same pattern we saw in the logit. For the lowest predicted probabilities, we're actually slightly under-predicting their chance of living. For the highest predicted probabilities, we're slightly over-predicting their chance of living. So not really getting much more out of this with the random forest. And in terms of predictions, we're getting bundles at 0 and 1. But in terms of classification decisions, we're getting a lot of similarity between the logit and the random forest. The logit's putting most of the same observations in the live box as the random forest. Just these and these little small sets of observations are classified differently. So that explains why we're not getting a whole lot different answers in terms of the performance. All right, that's CART and random forest models. I hope you enjoyed this introduction. And I do recommend, if you've watched this video, that I'm going to do a subsequent video shortly examining in greater depth these discrete choice model fit statistics, fit assessments that I've done. It'll probably be a short video talking about things like the percent correctly predicted, the expected percent correctly predicted, the Hosmer-Lemeshoff statistic, and the heat map fit statistic, all of which, well, at least two of which we alluded to in today's lecture. So if you've watched this lecture, you may be interested in that one as well, and I'll be posting it pretty soon. Until next time, see you then.